In this assignment, we will explore properties of operations that are important when we prepare data for modeling. So to get started, let's first create a new map set for our assignment 2, because we will be generating a lot of new map layers. So let's right-click on the project name and create new map set. We can call it assignment 2. And we can now start working. So the first task that we need to do to make performing the tasks easier is we should set the working directory in a similar way as we did in the previous assignment. So I have created it under documents, and you can create a new subdirectory as suggested in the assignment. So let's do it that way. Homework 2. So now all the images that we will save will go to this directory. So the first task that we will be exploring is resampling raster data to a different resolution. And we discussed it that we need to distinguish between continuous and discrete data. And we will also look at how different methods perform when resampling these different types of data. So let's first set region to 30-meter resolution, which is stored in a predefined region called Southwest SW Wake 30 meters. So we can just run it through command line, and we can display a 30-meter digital elevation model that we will be resampling to lower resolution, to higher resolution. So we can display it by double-clicking on it, and it is automatically added to the layer manager. Or we can run this command. Now to resample this digital elevation model, and we can just double check its resolution. You may remember that we find the resolution of that raster by running the metadata. So it is 30-meter resolution. So before we resample it, we set the region to the desired resolution. And in our case, it will be 10 meters. So let's just set our resolution to 10 meters. So you can see now, instead of 30 meters as shown here, it is 10 meters as shown here. And now we will run a resampling command that will resample this 30-meter resolution DEM to 10-meter resolution DEM. And when you look at the manual page, and it's linked here, let's open it in a new window. You can see that there are several methods that you can use to resample. And we will compare the outputs of these methods. So the first resampling we will do with the nearest neighbor, and the second one with bilinear interpolation. So let's just run this. And again, you can run it through graphical user interface. And the resampled DEM shows up. You can see that now we have two of them. And it looks very similar, like the original one, when we display it just by color. So to check for its structure, let's look at the aspect. And you can also do it in 3D, or you can do it running a hillshade. All of those will reveal the structure of the digital elevation model. So now we are taking the resampled DEM that we resampled by nearest neighbor, and we will compute and display its aspect. And when you look at this DEM, you can see that it has some artifacts. So you need to look back at the lecture and try to explain why do we see these artifacts when we resample this digital elevation model using the nearest neighbor technique. And let's just save this file for your report. And based on the resolution of your screen, you may see slightly different pattern, but it will have these artifacts as well. They may be farther apart or something like that. So now let's do this. Let's do similar operation, but using the other methods that are available in in the interpolation tool. So let's try bilinear and bicubic, and let's check it again using the aspect. So we will be resampling the DEM, and then we will be computing the aspect so that we can better evaluate the properties of this DEM. So again, it's bilinear resampling. It looks very much the same as the previous ones. Again, the one that is interpolated or resampled by cubic interpolation, again, it looks very much the same. Let's look at aspect. Now the DEM that was resampled using the bilinear interpolation doesn't have those stripes, those artifacts. So it looks much better, has much better properties if you want to use it as input for modeling. And here again, we have, this is the bicubic interpolation. And again, we don't have those artifacts, and we have slightly different structure, but much better representation of the properties of that digital elevation model. So let's just save at least the bilinear output, but you can also save the bicubic and discuss it in your report. So let me save it. And again, you can always save it using this icon. And as you can see, I already have it there. So pay attention to the questions that are highlighted in red, and we are asking you here to explain why do I have artifacts when we do the elevation using the elevation resampling using the nearest neighbor method, and why the bilinear interpolation is better for resampling. So this was resampling from lower resolution 30 meter to higher resolution 10 meters. Now, what we often need to do is that we won't be using we need to resample to lower resolution. So in our case, in our example, we will go from 30 meter to 100 meter. And so let's try it with our data. And now we will be doing it with elevation data, but also with discrete data with land use. So first, let's just remove all the files that we have in the layer manager. And let's display again our 30-meter DEM and also the land use map, which has resolution close to 30 meters. It's about 28 meters. And now we will use different techniques to do the continuous data, to resample to lower resolution, the continuous data and the discrete data. And you should explain why we are selecting these different aggregation methods when going from 30 meter to 100 meter resolution. So let's look at the elevation data. So we will be resampling to 100 meter resolution. So we need to set the region to 100 meters because that's the resolution of our computation. And then we will use, in this case, average. So that means that we will take several 30-meter grid cells and compute the average to estimate the value, elevation value, for at the center of the 100-meter grid cell. And you can see, like, overall, it looks the same as the previous one, but because the resolution is so low, we can now see the raster pattern in our output. So we don't need to rerun this drast command, but let's save it for your report. So we don't need this one. So keep that in mind when you keep the importance of selecting the proper method, when you will be, for example, preparing the data for your project, when you need to integrate data with different resolutions, what type of data it is, continuous or discrete, and what technique you need to use to properly resample the data. So let's now look at the discrete data set. That's the land use. So we will remove the elevation data. Oops, sorry. So we have lost some detail, but this may be necessary. For example, if you are going to use MODIS data or some other climate data that are coming, let's say, at 100-meter resolution, and you don't have them available at 10-meter resolution. So, and you will be running it for the entire United States. So you may decide that the optimal resolution for your modeling effort would be 100-meter resolution. So you will lose some detail, but the method for doing this resampling is mode. So you will be, again, for several grid cells, you will be replacing the values in several 30-meter grid cells by a single value in a 100-meter grid cell, and you will be selecting the mode method. That means the majority, essentially the value that the majority of those smaller cells had. And we don't need that one, but we want to save that file. Let me just save it. I need to overwrite this one. Okay. So then another task that you may need to do when integrating data from different sources for your project, or when modeling and combining data and outputs from different tools, is converting data from vector model to raster model. So in the first task, we will be converting the schools points representation to raster representation. And we will select, because this will be like individual points, so they will be represented by individual grid cells, while everywhere else where there are no schools, we will get null data. Then we will select a relatively low resolution so that we actually get like a more area representation of that of the schools. So let's just remove what we have there. Then let's set the resolution to 200 meters. You can see that at 200 meters for this spatial extent, we have very few rows and columns. It's only 68 times 75, very few grid cells. And what we will be doing, we will be creating a raster file that represents the capacity of each school. So now, instead of having points and many attributes in an attribute table, we will create a single raster layer that will represent capacity for each school. And this raster can then be used in a pretty sophisticated, complex analysis or modeling where the capacity of school will be an input variable. So first, let's display those schools. And we already displayed them in our first assignment. Then let's look at these variables, whether we indeed have that variable there. So it is here, core capacity. And now we have the raster resolution set to 200 meters. So we will convert the points to 200-meter raster. We will be using for the conversion attribute, and that attribute is called core capacity. So now we got a raster map that has lots of nulls, but in those locations where we have schools, we got a raster map that represents the core capacity of these schools. And you can see that it's mostly the same. There are some schools that have lower capacity, and you can add a legend so that we actually see what those numbers mean. So again, like we will be working with the legends later on, but you can put that legend, for example, here. So the capacity actually goes from 0. So the darker blue is smaller capacity, while the yellow and green is probably high schools. And we can just display the streets just for orientation so that we can see where these schools are. Oh, and here I have the legend as well.
Right.